Alright, let's get started with the solution for exam 3. Well, the first question says, discuss two economic motivations for offering variety other than price discrimination. Well, there are some really easy ones. The first one is so that you could sell in multiple channels. Remember the example I gave you, like companies have the same product but they want to sell in multiple, say Walmart and Home Depot. They just make it two different names, or Model A versus Model B. So one way, and sometimes they offer variety so that they can attract variety of customers. There were quite a few, and you can go back to the slide and look for this. And this is a pretty important idea, and I think this might be something you might be careful about for the final exam. Alright, let's look at this numerical problem. In this numerical problem, there are three steps: step 1, step 2, and step 3. Each of this step has a setup time, and each of this step has a processing time. And I want you to find the bottleneck if the batch size is 100. Alright, let's go and take a look at this. The formula for capacity in the presence of setup is straightforward. The capacity is batch size divided by setup plus batch size times the processing time. Well, the batch size is 100, right? And the setup in this case is 40 minutes plus the batch size is 100 times the processing of 0.3 comes out to be 100 divided by 40 plus 100 times 0.3 is 30, 100 divided by 70, right? Let's do this for this case. Again, the batch size is still 100. The setup in this case is 35 plus the batch size is 100. The processing time is 0.25. So this comes out to be 100 divided by 35 plus 25 is 60, right? In this case, the batch size is 100 again. The setup time is 70 plus 100 times 0.2 equals to 100 divided by 90. So you can tell the third step has the lowest capacity because everybody has 100 on the top, but this is the biggest number. So you can do the math if you want to. This comes out to be the lowest capacity. So step C is your bottleneck, right? The next question asks you what is the process capacity if the batch size is 100 parts. So, well, to find the process capacity, you need to find the capacity of the bottleneck. The capacity of the bottleneck is 100 divided by 90 units per minute, but the answer is required in units per hour. Well, to go from units per minute to units per hour, all you got to do is 100 divided by 90 times 60 comes out to be approximately 66.67 units per hour. That was easy. Alright, let's get to different one. Let me use green now. So what is the process capacity? The batch size is 500 units. Again, it's same question, do it again with B equals to 500. But the idea here is but by the time you do the first time, you can develop the intuition that no matter what the batch size is, this is never gonna be bottleneck when step 1 is there. Because remember, look at this, the setup time here is bigger in this case than step 2. Even the per unit processing is also bigger in step 1 than step 2. So when step 1 is there, step 2 is never going to be bottleneck because it has a smaller setup time and it has a smaller per unit processing time. So you really don't need to test 2. Well, 1 and 3 is where the real comparison lies, because step 1 has a lower setup time and step 3 has a higher setup time, but step 3 has a lower processing time compared to step 1. So you really don't have to compare 1. If you don't believe me, you can go ahead and do it for all 3. but I'm going to use this slightly faster, where not test step 2 anyway. You know it's never going to be the bottleneck. So let's test the remaining two, step 1 and step 3. Which one would be the bottleneck if the processing time was, if the batch size was 500? Well, in the formula is again the same. When the batch size is 500, let's do it for step 1 is 40 is the setup plus 500 times the processing time of 0.3. So it's 500 divided by 40 plus 150 equals to 500 divided by 190. Well, this is approximately 2.63 units per minute. Here again the batch size is 500. 70 plus 0.2 times 500, so this is really 500 divided by 170. Well, we know 500 divided by 120 is going to be bigger than 500 divided by 190, so we know that this is the bottleneck, or step 1 is the bottleneck. So making this the process capacity, but again we want the answers in terms of units per hour, so let's convert this into units per hour. So 2.63 times 60 comes out to be about 157.8. I mean, again, because of rounding, you might have a slightly different answer. Units per hour. All right. Assume that due to innovation in the industry, no setup is required in 1 and 2. What should be the best size? Again, this is if you can't see it right away, the best way is to make the picture again. The processing times is 0.3, 0.25. Here it's 0.2, but there is a setup of 70 minutes. Okay, everything is in minutes. Remember, the setup time here and here does not exist anymore. So this becomes a simple task. Here the capacity is going to be 1 divided by 0.3. Here it's 1 divided by 0.25. Here we have to find the capacity doing depending on what the batch size is. Well, we have to find the bottleneck, or the lowest capacity in between these two, to proceed. So this comes out to be 3.33 and this comes out to be 4. We know that if this part did not exist, then step 1 would have been the bottleneck. We knew that to begin with anyway. Now we can find what would be your optimal batch size. To do that, you have to take the slowest step among the one without the setup and match it with the one with the setup. Well, that means our target capacity is, let me use a different color here, our target capacity is 3.33 units per minute. That's our target capacity. And to get that target capacity, we want to find the batch size here. We know the setup is 70 minutes, plus we know batch times the processing time of 0.2. So to get this target capacity of 3.3, what should be the batch size? Well, you can solve this. 3.33 times 70 plus 3.33 times 0.2 is 0.66. B equals to B. Then you can solve for this. 3.33 times 70 is approximately about 233, and 3.1 plus okay, B minus 0.66B, or B1B minus 0.66B is 0.33B equals to, again, that depending on how well, it's really 0.33 repeating B minus equals to 233.1, or B equals to 233.1 divided by 0.33 repeating It comes out to be about, I took 0.33, I mean you could take 0.34, doesn't really matter, approximately about 706. Again, answer could be different depending on how you round up things. Okay, so what this is saying is you have to have a batch size of about 700. Then if there was no bottleneck and if there was no setup time here, having a batch size of 706 would make this and this bottleneck together, right? Making this the maximum capacity you can get with the minimum amount of inventory possible. All right. The next question is, this was a rather tricky question. First, we're going to find out the best way to do this is to get the Q star. You need 2 ds divided by the holding cost, right? That's what you need, cost of holding. So we're going to find the capital D first. The capital D is C uses $50 of printing paper per month. So 50 times 12, so 600 is your capital D. Okay, we've solved that part. Setup cost is usually given pretty easy. That's the ordering cost. So ordering cost is 85 per delivery. So S equals to 85. Usually the hardest one is the holding cost. Well, there are two holding costs here. One is the physical act of holding, and that is $1 per month. Remember, holding cost has to be expressed in terms of per unit per year. So that means a box to hold for a month is $1. 12 months is $12. The physical act of holding costs $12 per month, per box per year, right? Now there is another part of the holding cost. Remember, inventory cost is always a part of holding cost. That is, it is 2%. The capital cost is 2% per month. It's 2% per month. That means it's 24% per year, right? 24% per year. 24% of what? 24% of $12 per box, right? So that comes out to be $6. 24% of 25 is 6. So that means it cost $12 of physical act of holding and $6 the cost of money, $18 to hold a box for a year, right? Per box for a year. All right, now we are ready to calculate Q star. After this is just plug and chug. 2 ds divided by ch. 2 the yearly demand is 600 times the setup cost is, or ordering cost is 85, the holding cost is 18. You can solve this. It comes out to be approximately 75 point something. I just round to make my calculation a little easier. I just rounded it up to 75. All right, given your EOQ, how many times do you have to order? Well, you're gonna have to order 600 a year. If every time you order 75, approximately it comes out to be about 8, right? All right, what's Linda's total holding cost? Now we are thinking about is every time you order 75, that means your average inventory is 75 divided by 2. This is your average inventory. If your average inventory is 75 divided by 2, that is, and then 75 divided by 2 is 37.5. And to hold 1 unit for the whole year, you know it costs $18. So 37.5 times 18 comes out to be about $675. The total holding cost is about $675. All right, the next question is, so this Sarah's organic shop has 4 products. So she has to make A, switch from A to B, make B, switch from B to C, make C, switch from C to D, produce D, switch from D to A. So C has to switch once, twice, thrice, 4 times. So 1.5, 1.5, 1.5, 1.5 equals to 6 hours. Okay, all switching time is 6 hours. We also know she has to produce 150, 120, 75 and 50. So she has to produce at the rate of 150 plus 120 plus 75 plus 50 comes out to be about 395 kilograms per hour. That's the speed she has to target. Okay, her processing capacity, her processing time is, given that she can produce 400 kilograms per hour, it is 1/400 per unit. Well, we are ready to calculate the batch now. Okay. Well, this whole cycle, what amount of units, how many kilograms of the all products he has to produce in the cycle is given by our target capacity is 395 kilograms. So let me use a slightly better color here. 395 kilograms per hour. We want to find the batch, or the whole cycle, if you will, the setup plus batch times the processing time. This 395 equals to the batch is what we are after. The setup is 6 hours plus batch is what we are after. The processing time is 1 over 400, right? Or 395 times 6 plus 395 divided by 400 b. If you multiply b by 400 with 395, this is what you get, equals to b. Or 395 times 6 is 2370 plus, now you can take this b and b in the same side. Well, you really don't need the plus. Okay, b minus 395b divided by 400, or if you just bring this b, so this is really 1b. 1b is same as saying 400 by 400b. So 400 by 400b minus 395 by 400b is just 5b divided by 400 equals to 2370, or b equals to 2370 times 400 divided by 5 comes out to be about 189,600. So this whole batch is 189,600. Okay. Now if she is producing 189,600, what is the size of the regular? Regular is the one that was 150. So out of 395, 150 was regular. So out of 189,600, it is about 72,000. Right? 72,000 kilograms of regular before switching to another scent. How long does it take to complete one full cycle? Well, there are many ways to do it. You can look at this whole thing and you can say, okay, how much AC has to produce, then the switch of 1.5, how much BC has to produce, and how long does it take, and all these things. But the easier way to think about this is, remember, altogether in one cycle she has to produce 189,600 kilograms, and she can produce at the rate of 1 over 4. It takes you 1 over 400 hours to produce 1 kilogram. Or another word is say, in 1 hour she can produce 400 kilograms. So to produce 189,600, it takes her 474 hours, and there is 6 hours of switchover time, so 480 hours. All right.